Very pity that many students cannot attend today class. Just 45 students. What happened? I don't know. Okay, can you see screen? Is it okay?
Yes, okay.
Okay. Please. Sometimes you make voice. Otherwise, I don't know. You are hearing me, seeing me well or not. I do not know. That's not good. Okay, let me explain the previous topic a little bit and go the continuation. Today, actually, we are very interesting topic we discuss. Very interesting and very useful. And questions for the final exam. We have 2 questions from this chapter. So that's why it is very important chapter. So please do be active, and if you not understanding anything, you please stop on the way. So I hope you can see. Okay. So now in the previous class, we have started. What is the open set? Huh? Okay, just as a revision, open set is a set such that open set. So today we start the set theory actually. Set theory. You have familiar with the set theory, but here we have more proper, more complicated studies we study. Definition says, let E be the subset of real numbers R. The E definition says, definition 1. Let E be the subset of R of real numbers. A point X, a point X from E is said to be interior point. Is said, because this very important definition is said to be an interior point, a interior point if interior point of E if there exists epsilon, positive epsilon, very small, such that this interval x minus epsilon, x plus epsilon belong to E. Okay, or is this is a subset, not belong. It is this one is a subset of that's difference. It is a subset of RE. Okay, so imagine actually in general I can say like this. This one I will put on the top. So this is the set E. Okay, this is the set E. So interior point means any point which is close or far from the border, doesn't matter, but the any point with the epsilon neighborhood, of the point X belong to the set E, not out, not out point. Just even it is very close to the end point, but this epsilon we can choose such a way. Therefore, they say there exists epsilon such that the epsilon neighborhood of X is a subset of E. Okay. Now there is very interesting point. For each cases, we consider the following sets. Okay, one by one, you will tell me. So n is the natural number set, huh? Natural number set. Second one is z, integer number set. N minus union 0 and union n plus. This is the z. So number 3 is q. Q usually consists of P over Q or A over B. I usually like P over Q, such that it is a rational number. It is a rational number such that P and Q belong to Z, but Q cannot take 0. So this is a natural number set. Number 4, the R. R is the rational number set union a rational number set. A rational, currently I just denote by the P. Okay. And one more thing, we usually take some set as a interval. For example, A, comma, B, and just like this. Okay, the half interval. Closed interval. Okay, according to this definition, we have already discussed it in the previous class. So what about n? Does n have interior point? We have discussed about it. Does natural number set has interior point? Hello, please let me tell me your opinion. Does n has interior point? Hello. Please say something. Does it have interior point?
Yes, maybe.
Now, in mathematics, we don't say maybe. We say yes or not. If you say yes, you need to prove it. How you prove? Okay.
I'm not sure that how.
Oh, look, look. Here, I am saying epsilon neighborhood of x should be completely belong to E. For example, if I take one example, 1 minus epsilon, 1 minus epsilon, and 1 plus epsilon. You see, small for the small epsilon. Can I say this interval, you see, 1 minus epsilon, 1 plus epsilon, can I say it is a subset of n? Imagine. So I choose just one point and take the epsilon neighborhood. Can I say, so this n, this epsilon neighborhood of 1 belong to the n? Definitely no, right? Because the epsilon neighborhood of 1 contains many rational number and many irrational number on the left side, on the right side, except n. Except n. It definitely doesn't belong to n. You see, it doesn't belong to n. So the one, you see, if I show 1 point is not this epsilon neighborhood not belong to n, then instead of 1, I can take any n, any natural number, and I can say this neighborhood of any n in n. You see, this n belong to the n, but epsilon neighborhood doesn't belong to the n. So it means the none of the point is not interior point. Okay? Did you understand? Hello?
Yes, sir.
Okay. So now the same thing goes to the natural integer number set. N minus epsilon, n plus epsilon doesn't belong to doesn't subset of z also. So there is no interior point in z. Okay. What about q? Is there any? Q is a rational number set, which means very dense set. You know, natural number set, integer number set is not density. It is, random. There is a big gap between them. But the rational number set is very close to each other. There is no gap there. Yeah, not I cannot say no gap, but they are very dense. What about here? If I take any rational number, for example, 1 over 2 is a rational number, minus epsilon, 1 over 2 plus epsilon. Okay, 1 minus 1 over 2 plus epsilon. Can I say it completely belong to the Q? This epsilon neighborhood belong to. So no more. If you are coming in, I won't allow you. Already half hours that gone. Epsilon neighborhood of 1 over 2. Can I say that this epsilon neighborhood completely belong to the Q? Because they are very dense. My friend, what is your opinion?
Subset. Q.
Huh? Can I say that this Q has interior point?
No.
Oh, somebody says no. Correct. Correct. Why? Because this epsilon neighborhood, please, for every cases, every definition, we will check with these 5 examples. Imagine we have straight line. This is a R, and I'm taking one rational number and taking epsilon, very small, but epsilon neighborhood. In the epsilon neighborhood of 1 over 2 contains rational number and irrational number, right? Because the every rational number next has irrational, next is irrational, next is irrational. Actually, irrational number is more than the rational number. Maybe, after one rational number, the next is also a rational number, next is rational number. But any point, epsilon neighborhood of the point, you see, contains rational number and irrational number. So therefore, this neighborhood doesn't completely belong to the Q. It means it is not exactly Q. So there is Q, the rational number, there is non-Q. So it means this neighborhood doesn't completely belong to the Q. Did you understand? So this Q has no interior point. You see, already he has stated the nature, this N has no interior point. Q has no interior point, but I am explaining with the example to be clear. To be clear. Got it? The idea? Now I am coming to the R. R. So for the R, I can take any point, an epsilon neighborhood. This epsilon neighborhood completely belong. You see, the any x from R and taking the epsilon neighborhood, whatever small, doesn't matter, x plus epsilon, this interval, of course, completely belong to the R. X can be any. So every point in R is a interior point. You see, when we come to the R, so every point is the interior point. Okay, this one correct. So particularly, for example, 1 over 2, epsilon neighborhood of 1 over 2 contains rational number and irrational number. So rational number union irrational number is real number set. So that's why this belongs always correct for any x, not only 1 over 2, any x on the line. So the R is every point of R is an interior point. Okay. So now last one. What about this A? If I take any x from A and neighborhood of x, can I completely belong to the A or not? How do you think? Do we have any point not belong to A? The epsilon neighborhood not belong to the A. Hello? Do some answer. Correct or not, I will answer. Every point of A, if this one correct, you look, if this one correct, then I say every point of A is the interior point. Hello?
Yes,
Yep.
maybe.
Again, friend, don't say maybe. You say yes or not. Even wrong, just answer one, not maybe.
No.
Yes or not?
Yes, doctor.
So the one girl says yes. What about you, friend? Yes or not?
No.
No. Yes, your answer is correct. Okay, look. I'm taking the point from this interval. Okay, when I cannot take A, but very close to A. I can take very close to A. A minus plus delta. A plus delta. Delta is very small because X cannot be taken as A, but very close to A can taken. Now I'm taking the epsilon neighborhood. A plus delta minus epsilon. A plus delta minus epsilon. So now look, I can say this one equal to A plus epsilon 1. Sorry, this is second one is B. The A, this is correct. A plus, this is plus epsilon. This is plus epsilon. So this one, A plus epsilon 1, and this one, A plus epsilon 2. Epsilon 2. So can I say this is completely belong to the A? You see, I am taking very close to A. You see, because epsilon is in our hand. Epsilon, I can choose such a way it is less than delta. If less than delta, then epsilon 1 is positive, which is delta minus epsilon is positive. So this epsilon 1 is positive. And epsilon 2 is definitely positive because delta is positive, epsilon is positive, so it is positive. You see, I can find positive epsilon neighborhood of A, you see, of A, such that it completely belongs to the A. So that's why this every not every point actually, the close to A is interior point. Now I am taking the boundary point of B, x equal to B. When x equal to B, then epsilon neighborhood of x, which is B minus epsilon, B plus epsilon. Can I say this interval is completely belong to the A? Can I say? I am taking the B, you see? So this is A. So this is B. I am taking that point B and taking epsilon neighborhood. You see, this is B plus epsilon. This is B minus epsilon. Can I say that this interval completely belong to the A? Brent, answer something. Yes or not? Hello? Yes or not?
Yes.
Yes? Okay, another alternative answer? Just now one girl also involved very well. Yes or not for you?
Yes, doctor.
Also yes. Hey, please pay attention. I am drawing the graph. You see, this is a B. This is a B. Then I am B plus epsilon, B minus epsilon, considering this interval. Look, this is the interval. Is this interval completely belong to the A or not? From the our A is from A until B. This is the A. This is the A. Starting from A, ending with the B. Beyond the B, it cannot take. Can you see from this graph the epsilon neighborhood of B completely belong in A or not?
No.
No, yes, no, cannot. This one cannot. Doesn't satisfy. So that's why for the A, the set A, look, for the set A, I can say, so all point from A is interior point, interior point, except x equal to B. Or I can say interior point of A, because there is a notation, interior collection of all interior points is equal A, B. You see, A, B, from starting A until the B, every point on this interval is an interior point except B. You see, except B. Could you understand what is the interior point? I hope very clear picture now, huh? So, okay, let me go to the next definition. Because if you understand very well the definition, then your imagination will be better and can solve some complicated problems. Okay, what about a second example, second definition? Let A be the subset of real numbers. A point X is said to be boundary point of A if for every epsilon, the open interval, so epsilon neighborhood, open interval, contains at least one point of A and also at least one point that doesn't belong to A. So now interior point, point done, boundary point. So the definition 2 says, uh, a point X, any point means a point X uh, from A, from A is said to be boundary point. Okay, a point from A point X from A is said to be boundary point, boundary point if boundary point of A, huh? Boundary point of is said to be boundary point of A uh, if for every, you see, for every epsilon, the open interval, this open interval contains, this open interval contains, not contain it, contains at one point, at least, okay, at least, actually this one also is needed, at least one point of A and one point uh, one point that doesn't belong to of A, and one point out of A. I shortly out of A. Okay, so that is the definition of the boundary point. Okay, let us check the above 5 sets. Okay, this is a definition. Okay, the first, taking this n, natural number set. Okay, according to the definition, I am, for example, taking x equal to, let's say, 1. So 1 minus epsilon and 1 plus epsilon. I'm considering that the point. If for every epsilon, so this interval contains at least one point of A. You see? So this one contains element 1. So element 1 belong to this set. And this one belong to n, belong to the n. So at least one point is taken from n. Now, on the other hand, 1 minus epsilon, 1 plus epsilon contains another any point, for example, A, not belong to n, not belong to the n. For it, depending on the epsilon, I can choose a lot of point. Doesn't belong. Okay, doesn't belong. Point A, you see, yeah, A is, no, sorry, here A is, this is belong. It is containers, the number A, which is not n, but belong to this interval. Okay, so number one is a boundary point. Similarly, I can take the number 2. In general, I can take any n from capital N such that this n minus epsilon, n plus epsilon contains at least one element in n and one element out of n. One element out of n. Okay? Could you understand? So the one element which is not belong to the n. You see? So it means that every element of n a boundary point. Every element is boundary point. Every element is boundary. Okay, every element of n is boundary element. So because we are boundary point, not element, boundary. Every point is a boundary point. Could you understand? Okay.
Yes.
Similarly, for the Z, I don't want to explain because it is the same as this. Huh? So blah, 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 -2, -1, 0, 1, 2, and etc. So this element also, every element of Z is boundary point, Okay, you see here, in the previous day, there is no interior point in N. There is no interior point of Z. But when we learn the boundary point, so every element of natural number set is a boundary point, and every Z is also boundary point. What about Q? Q. How do you think? It is P over Q, PQ, this is such that PQ from Z except Q not equal to 0. Okay, this is a rational number set. What about this? If I take just one x equal to, for example, 1 over 2, in order to be clear, 1 over 2 minus epsilon, 1 over 2 plus epsilon, this interval, can I say contains rational number belong to the Q? Yes, definitely. For example, 1 over 2 itself is a rational number, and this rational number is in the interval. This interval contains at least one point from this, and this interval, actually this interval contains a rational number as well. Okay, a rational number. So since it contains a rational number, there exists B not belong to Q. Not belong, but B is in here, but not belong to Q, because epsilon neighborhood contains a rational number and irrational number. So therefore, there exists number B, which is not Q, but belong to this interval. So you see, every point, now I can make conclusion, every point of Q rational number is boundary point, Okay, look here, also stated, every point on the real line, both rational and irrational, is a boundary point of the set Q. You see, every point of the every point on the real line, both rational and irrational, therefore it is a boundary point. So Q, so every point of Q is boundary point. What about the previous definition? We say none. You see, look, next, none of the point of Q, none of the point of the Q is not interior point. It wasn't interior point. There is none interior point. But now, after the definition of the boundary point, so you see the totally different situation. Every point of Q is a boundary point. None of the point is interior point. Okay? Can you imagine well? Hello? Are you awake or sleepy?
Yes.
Okay, good. My friend, sometimes I say something. If you have questions, please stop me. Okay, next. What about this? The R is okay. The R always we have. So this interval. Okay, this interval. What about the boundary point? Previously, we have shown interior point of A, look, interior point of A was open interval. You see, all the point of A is the interior point except B. Yeah, sorry. Here should be like this. So A like this, B like this. So A is open, B is like this. So interior point of A is both like this. Now, if I take x equal to B, okay, and consider the interval epsilon, sorry, B minus epsilon. If I take the x equal to B, B minus epsilon, B plus epsilon. Okay, I'm taking this interval. So this interval contains element of uh, so B look at least one point B is in here and B is in the the A belong to the A. Now on the other hand, this interval contains another element C which is not belong to A. You see? So it contains any element C not belong to A, but it contains here. So this C definitely, so this is A and B. Okay, now look, the B plus epsilon is here. So C must be between B and B plus C. Okay, it cannot be beyond this. It should be between them. So this C belong in this interval B to B plus epsilon. So it is not belong to A, but it is belong to this interval. This is B minus epsilon. Okay. So what is the conclusion? Boundary now. Boundary BD, boundary point of A is only one point. You see, all points was interior point. You see, all the points except B was interior point. Now, boundary point of A is only one point. That's all. No more. According to the definition, I have identified that A has only one boundary point. Got it? Hello? Got it?
Yes, sir.
Okay, good. Okay, now definition of the boundary point is also clear, huh? Definition. So then it's said to be, okay. Then next, the boundary, the definition of the boundary is clear. Next definition, let E be the subset of real numbers. Then E is said to be open, if every point of E is also interior point of E. You see, a set E is said to be open if every point of E is an interior point of E. Okay. Now, this, if I'm talking about the A, this, can I say this this interval is open interval? Can I say this set is an open interval according to this definition? Can I say this A is open interval? Open set. This is this definition says about the set. A as is a set. This set is said to be open if every point of E is also interior point. Is open set. Can I say like conclusion like this? Hello.
Yes, doctor.
Can I say A B is open set? My friend, What about your opinion? Can I say it is open set?
Yes.
Ayo, you are also making same mistake as the girl say. Look, just now we have proved it. There is one boundary point. Okay, there is one boundary point. So it means not every point of A is an interior point. Look, interior points, the collection of all interior points, we have proved it. It was like this. You see, B B is not interior point. Okay, is not interior point IP. You see, for this case, this set is not open set. If one point doesn't suit, we cannot say this one is open set. This set is not open set. Later on, you will see this set is not closed set as well. Okay, currently this set is not open set. Okay, your answer is not correct now. What about this set Q? What about Q? What about Q? How do you think? Can I say uh, interior of Q? Interior of Q? What about interior of Q? Already we have discussed it before. Interior of Q was empty set. Okay? And boundary point of Q was every point is Q. Boundary. Every point of Q is a boundary point. We have proved it. Interior point, empty set. There is none. If there is none point is interior point, definitely this set is not open set. So Q is not open set. Is not open set. Understand? Q is not open set. Definitely N, Z are not open set as well. Only the interval, you see, interval, this interval is not open set. If I can consider AB, then it is open set, of course, open set. So open set depend on the interior points, you know. If interior, every point is an interior point, then this set is called open set. Got it? I hope you understand. Okay, next. Here another interesting point. Please pay attention. Empty set is open set. Since it contains no elements or no points that are not interior point of the set. You see, interior all the points in the empty set is a interior point because there is no element, and therefore every element in the set is an interior. So that's why it is an open set. You see, empty set is an open set. Got it? What about R? What about R? Real number set? From minus infinity to plus infinity. So this set is open set. Because every point is an interior point. Open set. So R is an open set. This interval is an open set. Look. You see, whole element is open set. Okay, this you see not including the boundary, is the open set. In R, there is no more. The empty set is a empty set is open set.
Doctor, I have a question.
Yes, welcome.
If let's say the empty set is called as open set, then why not the Q, the rational number is not an open set?
This is very good questions. Look, the rational number set, we have shown there is no interior point. You see, every point is not interior point in Q. A definition of the open set says every point must be interior point. If there is no interior point, then of course we cannot say this set is an open set. To be open set, every point must be open, must be interior point. Okay? You see, the Z is very Q is very dense set, but none of the point is not interior point. If there is no interior point, we cannot say about the open set. To be open set, every point must be interior point. Okay? So let me on. Any questions? Okay, just 5 minutes. You can rest. Then we will continue. Okay. So if you have any, just a few minutes of discussions, what I am planning actually, tomorrow I will bring the questions, I mean the assignment. Okay, assignment. So we discuss about the assignment. Now, the Miss Anne, you have to collect the group of the students. So you have the 71 students in total. So if every 5 students are one group, around 4, 5, actually minimum 5. So around 12 groups. You please collect the 12 groups. Miss Anne, are you here?
Yes, doctor.
Okay, please be active. So please collect the 12 groups. Each group consisted of 5, one group 6. So will be 70, will be the 12 groups. So tomorrow I will distribute and explain how to make the assignment. Okay, assignment I will give tomorrow. Or next week also okay, because still we have enough. Actually, this week is a week 9 or week 8
Week
in
8.
teaching. Week 8, huh? Okay, if week 8, actually for that one we have enough time. maybe not tomorrow, the next Sunday, I will bring the proper, because I have enough questions for 10 groups. So another 2 more groups I should extend. So what I'm going to do, I'm giving for each group around 6 questions, I think 10 questions, okay, from different area of a subject, this chapters, and every group will solve around 10 questions, different questions. I will questions for 12 groups. So from the different topics in our group, so that you will work on the questions, okay? Then collect all the solutions and submit as a report. Then you will present it. Presentation will be evaluated, 1, and the report will be evaluated, 2nd. So actually for assignment, how much I gave? If I'm not mistaken, 10 for the quiz, 20 marks for midterm exam. So 20 marks is for assignment. Okay. So I think 5% is for the presentation, 15 is for report. Okay. Actually, tomorrow, inshallah, I will announce the first quiz. First quiz results, I'm surprising, very easy questions, but still some students get very low mark. I'm a little bit surprising if you are answering questions very not not, because quiz is very simple and easy questions I choose. And second one I will announce next week. So tomorrow I will bring the first results. It is almost ready. I need to type it and key in this. Okay, so far is okay. Now let me start again our class. Do you have any questions so far about boundary point, interior point? What else? Open sets. Currently now we stop on about the open sets. I hope everything's okay, because nothing difficult. So next, here example, you see open interval is an open set. Open interval is open set. Okay, because every point is an interior point. The closed interval is not open set, since they have the 2 boundary points, right? You see, to be open set, every point must be interior point. So this closed set, actually this interval is not open set. The set of natural number has no interior point. So therefore, it is not open set. Okay, it's not open set. Every point of R is the interior point. Therefore, R is open set. And very interesting point. Today you will come to the contradictions. So this empty set is open set and R is an open set. But later on we will prove R is closed set and empty set is also closed set. It looks like contrary, completely contrary prediction, but both of them are correct. You will see. Okay. Okay. Next definition. Let A be any subset of real numbers. Then the set interior of A denotes, yeah, you see, interior of A, already I have used it. Interior of A denotes the set of all interior points of A and is called interior of the set. So in this notation is called interior of A, interior of A. So it is a collection of all interior points. Okay, nothing here difficult to explain. Now interior of AB, look, is AB. Interior of AB closed, this closed interval is also AB. Interior of N is the empty set. Interior of Q is the empty set. Okay. Furthermore, interior of A is the open set since it is a interior of open sets. Okay. If G is open subset of A, then G, you see, here one more point. Interior point of A is the largest open set contained in A. Please pay attention. Interior of A is, look, interior of A is a subset of A, but it is the largest one. It is a subset of A, but it is the largest one. So if G is another open subset of A, then G must be, so G, if G is another open subset of A, so this G should be is contained in interior point of A, all the collection of A. So it must be in here. Okay, because interior of A is the largest open set in A. Open set in A. Okay. So accordingly, a set is open if and only if interior of A. Another interesting definition. The second definition. A is open if and only if interior of A equal to A. You see, if interior, we collect all the interior points, collect, and get the results. If the resulting of interior points is equal to the set, then set is open. This is another type of definition of open set. Okay, good. Now, next is very interesting, another definition. We are coming up. Let A be the subset of real number. A point X, not necessarily in A. You see, a point X from R, not necessarily in A, is said to be an accumulation point of A. You see, accumulation point of A. If for every epsilon, the open interval containing X contains a point of A different from X. Different from X. So this one is the accumulation point. Look, accumulation point. So for the accumulation point, we have the definition 3. Definition 3. A point X, but here please pay attention, not a point X from R, not from the A, from the set A. A point X is said to be an accumulation point, accumulation point if for every epsilon this open interval X minus epsilon, X plus epsilon, containing X, definitely this X is an element of this, containing X, contains a point of A, contains a point of A, so contains contains a point of A different from X, different from X. Different from X. In other words, this Actually, this is nice formula. A intersection of x minus epsilon, x plus epsilon, this interval, except x is not empty set. So this is the accumulation point. You see, the x may not belong to the A, but epsilon neighborhood except x intersection with A is not empty. So that type of point is called accumulation point. So another word, look, from calculus, I am just revising. For example, 1 over n. You remember an as n tends to infinity is equal to 0. So this 0 is limit point. We call it limit point. So actually, accumulation point is also some type of limit point. So another word, you see, why this 0 is a accumulation point for this set. You see, if I take the A is a set of an, which is 1 over n from capital N, then this set is a set of rational number set. Okay, you see, it has only one accumulation point here. Accumulation point is only one. Because limit 0 is accumulation point of A. Accumulation point of A. Only one point we have accumulation point. Okay, so another word, I can say, so any point x is called accumulation point if epsilon neighborhood of x, epsilon neighborhood of x, except x. Why here except x? Because this x may not belong to the A. So that's why. Contains infinitely many points of A. You see, contains infinitely many points of A. So it is this x accumulation point, actually the epsilon neighborhood contains many elements of A. But as a formula, this is nice formula to find the accumulation points. Okay, because next, just isolate points. I will give the definition of isolate points, and from there you can see the differences between accumulation point and isolate point. So let me give the definition of the isolate point, then compare each other. Okay, then we will consider the examples. After that, the set of all accumulation points denoted A prime. That one is A prime is the collection or the set of all accumulation points. Okay, next is isolate point. Please pay attention. What is the difference between accumulation point and isolate points? Definition 4. A point X, you see here, a point X from E. E is a subset of R. You see here, X belong to the E. Okay, is said to be isolated, to be an isolated point. Isolated point of E. If if there exists epsilon, please pay attention, if there exists epsilon. Here, for every epsilon, there exists epsilon such that this open interval x minus epsilon, x plus epsilon, open interval containing x, so x is in here, contains no other point of E. Contains such that the containing x contains, so this one contains no other point of E. So contains such element A which is only from E, only from E, no others than E. Okay, no other point of E, only from E, only here A only. So this interval contains only element of E. Another very nice formula. Actually, look, it is looks like the same as this, but totally different. So okay, now this is E intersection of x minus epsilon, x plus epsilon, except x is equal to empty set. You see, is equal to empty set. Or another word, I think the second one is more proper. The second definition formulas, E intersection this interval, this open interval, gives only element of x where x from E. This intersection gives only one point. Then it is isolated point. It's called isolated. You see, it is totally different than the accumulation. For the accumulation, A intersection with the neighborhood of x except x is not empty. Here it is empty, which is equivalent definition of this. You see, if I open up E intersection of this minus E intersection, look, actually E minus the E intersection with one point. E actually is x is the element of E. So that's why this intersection actually gives only one element. Because already we said x is belong to E. So E with intersection x, only one element. Of course, gives only one x. So that's why this x, if I shift to the right, so this intersection gives only one point. You see, if this intersection gives only one point, it is an isolate point. If intersection of A, you see, A intersection, if I open up this, A intersection x minus epsilon, x plus epsilon, then minus A intersection the one point of x. You see, this one, I cannot say this is equal to x. I cannot say this one is equal to x. You see, that's why this interval is not equal to, is not equal to just x. Here, I cannot open. I can open, but I cannot shift to the right because this one intersection of in the A, because this x might be belong to A, might not belong to the A. If it is belong to the A, then this intersection becomes x, and this x, if I shift to the right, what will happen? x minus epsilon, x plus epsilon is not equal to just 1 point of x. Look, if x belong to the A, then this definition becomes like this. So imagine E intersection with the epsilon neighborhood gives only 1 point. That is the isolated point. If E intersection with the neighborhood doesn't give the 1 point, which means many points, then it is called accumulation point. You see, these two definitions are very close each other, but there are big differences. Big differences. Okay, now example. Example. You will see the by example you can understand very well. Example. Okay. Let me take the n. So A equal to n, natural number set. Okay, please tell me, what about accumulation point of A? Accumulation point of A. How many accumulation points we have in n? By definition. So accumulation point is a point such that the epsilon neighborhood of x. Look, can you calculate this? To find the accumulation point, we should consider A intersection any x. For example, I can say 1 minus epsilon, 1 plus epsilon, except 1 is not empty set. Is not empty set. Can I? Look, A is a natural number set. If natural number set and 1 is here, look, I am taking the from here only 1 point from A intersection. If I am taking out 1 from this interval, it becomes intersection. Actually, that one becomes empty set. I'm taking any point from n, particularly 1, considering intersection with this 1 minus epsilon, 1 plus epsilon, then subtracting 1. You see, subtracting 1. Actually, it is better to say like this. Then it is empty set. I can say it is empty set. Am I right? Because intersection, I am taking 1 point and taking out this point, then considering the intersection. No, yes, look, I am taking out 1 and considering intersection with 1 of this interval. You see, 1 and intersection 1 minus epsilon, 1 plus epsilon. But 1 is not there. You see, if 1 is here, I will get only 1. But since I'm taking out this 1, taking out the 1, so the intersection is empty set. You see, according to the definition, according to this intersection shouldn't be empty set. Shouldn't be empty set. Now, in my case, 1 is a 1 intersection with this interval except 1 is empty set. 2 is the same. 3 is the same. So n natural number set has no accumulation point. Accumulation point, AP, has no accumulation point. What about isolate? For the isolation, look, n intersection 1 minus epsilon, okay, currently is an example 1 plus epsilon. So this intersection, if this intersection gives just 1 point, gives 1 point, okay, so this one gives only 1.1. Can I say, look, n intersection with this 1 minus epsilon, 1 plus epsilon. Of course, 1 minus epsilon is the interval, and intersecting with the n, only with the number 1, it can intersect. There is no other type. And that intersection is gives only 1 point only. Similarly, if I take n intersection with 2, I don't need the another extra bracket, because definition says a intersection of 2 minus epsilon, 2 plus epsilon gives only number 2, 1 point. You see, only 1 point. You see, every point of n is isolate point. You see, just now we have proved it, n has no isolate the accumulation point. Now n every point of n, every point of n is isolate points, isolated point. Every n is an isolated point. Okay, you see, n has no accumulation point, but n has every point of n is an isolate points. Okay, what about R? Okay, R. Can I compute R intersection with x minus epsilon, x plus epsilon, except x? Can I say this one is empty? Is non-empty? Is non-empty? Can I say? You see, x from R, because R is the whole numbers. Now epsilon neighborhood, except x, intersection with the R is non-empty. Every point is non-empty. This interval with intersection is not empty. So every point, every x in R is accumulation point. What about isolated? Okay, can I, this is the second one. I am taking the x from R, okay, and considering this intersection, x minus epsilon, x plus epsilon. Okay, this can I say this is equal to x. Look, R is a real number set. Of course, this intersection actually, if I calculate properly, it gives like this. This intersection gives interval x minus epsilon, x plus epsilon, which is not equal to x. So none of element of x from R is isolate point, IP. So there is no isolate points in R, but every point is an accumulation point. The last one, what about rational number set, Q? How do you think P over Q? Okay, P over Q. So if I consider this intersection of Q, look, Q intersection with the neighborhood of x minus epsilon x plus epsilon, subtracting the x, this, can I say it is not empty? It is not empty set. Please pay attention. In the accumulation point, the x may not be lying in the set. Look, x, a point x. You see? Not necessarily in A. So this x maybe belong to the A, x might maybe belong to Q, or may not belong to Q. So it means it can be a rational number, it might not be a rational number. But this intersection, if this intersection always non-empty, then we say X is a accumulation point. Now imagine Q intersection this interval plus minus Q intersection with 1 point. Okay, now imagine what can happen. This Q intersection with X can be equal to X, only 1 point, if X belong to Q. If X is a rational number, then this intersection gives only 1 point. Otherwise, it gives empty set if X not belong to Q. Can you imagine? So if X belong to the Q, this one gives X, gives. Otherwise, empty set. So in the case 1, when X belong to the Q, this intersection, Q intersection X minus epsilon, X plus epsilon, this interval. So equal to X. Am I right? Because this one X, which is not empty set, If on the other hand, this intersection, actually Q with the epsilon neighborhood of X, what does it give? If X not belong to the if X belong to the Q, so this intersection gives what? If X belong to the Q, this one is X. It is correct, just 1 point. But what about this interval? This interval, if X Q, of course, this one not empty set. It is not, I can say, not empty set. It is non-empty set. But if it is like this, it is an isolate point. Anyway, so every X, so this one non-empty. On the other hand, this one is X. So which is non-empty. So the case 2, if X doesn't belong to the Q, doesn't belong to the Q, then this intersection is empty set. If it is empty set, then Q intersection X minus epsilon, X plus epsilon, this minus this equal to empty set, equal to empty set, equal to empty set. So it means it is equal to empty set. What does it mean? Q with the neighborhood gives the empty set. Actually, if Q not belong to the Q, so this one still not empty set, because Q is a density set, and X minus epsilon, X plus epsilon also has the small interval, and intersection shouldn't be equal to empty set. You see, that's why this type of description may not be very clear. But look, Q intersection with epsilon neighborhood of any X, the epsilon neighborhood, actually is not empty. Is not empty set. This one always not empty set. Even we are taking out X or including X, doesn't matter. By the definition, we have to take out the X. So if this one not empty set, then Q is the every point X in Q are accumulation point. Actually, Q is a density set. Therefore, every point of Q is a accumulation point. Now, what about the isolate point? For the isolate point, we can easily get Q intersection with the X minus epsilon, X plus epsilon. This one, can I say equal to X? When is this one gives the only 1 point? This one never and ever be X, because Q is a density set. Then intersection with the epsilon neighborhood of X is not one point. It has interval, but with that interval contains only the rational numbers. So it means it is not equal to X. So it means there is no what we call it, definition, accumulation point, no isolate points in Q. There is no isolate point in Q. Here also, I think they have. Okay, look. Every point of R is a accumulation point. Every point on the real line, rational, is a accumulation point of the set. You see, the hence Q prime actually is what? We say that the set of all accumulation point of A denoted by A prime. The set of all accumulation point is denoted by A prime. And name it is derived set. You see? So for the so A prime is actually is a set of all collection of accumulation point. The set of all collection of accumulation point, or shortly derived set. So What about the derived set of n? Why it is equal to empty? Huh? No point of all is the accumulation point of the set of natural numbers. No point of accumulation point. So you see, there is no accumulation point in n. So therefore, the n prime derived set is empty set. It is correct. Every point of R is the accumulation point. So R prime is equal to R. Okay, every point on the real line uh, is a the rational number or irrational number. So that's why the Q prime derived set of Q is R. You see, here the Q prime is exactly equal to R. And here another definition is said to be the isolate point. Already I have stated. So you see, isolated point is, imagine it is a isolate point is, you see, the natural number set is a every point of natural number set is a isolate point. So it means this intersection gives only one point. If it gives only one point, that point is called isolate point. Okay, isolate point. Then accordingly, if x belong to the A, but x not belong to E prime, E prime is a derived set. Please pay attention. Derived set means the set of collection of all accumulation points. Okay. Now, no point of the open interval is a I. You see, it is correct. Huh? Open interval has no isolate points. Has no isolate point. Closed interval has no isolate points. Every point belonging to the set of natural number is an isolate point. No point of R is isolated. No point of Q is isolated. You see, no point of Q is isolated. But every point of Q is accumulation point. Every point of R is a accumulation point. So please pay attention. Knowing this, now we are going to prove very important and interesting theorem. Before the proof of the theorem, we need to know this definition, indexed set. Okay, what does it mean, indexed set of the indexed class of the sets? Actually, indexed class of sets is denoted by like this. Actually, usually we use like this. A alpha belong to delta. So indexed class of the sets assigns a set A alpha to each alpha belong to the delta. In other words, it is looks like function. Huh? The indexed class of sets is a function from delta into the class of sets. The set delta is called index set. This delta is called index set. Alpha is called index. A alpha is called indexed sets. Indexed sets. Okay, that's the name. So when the index set is a set of a natural number, the indexed class becomes like this. It's called sequence of sets. Please pay attention. Here, this one actually very often we use indexed set. Look, A in general, so this one is called alpha from some kind of, okay, this one is called indexed class of sets. Indexed class of sets. Class of the sets. Okay, now when delta, if delta equal to natural number set, then this set A alpha, instead alpha I will put n, an, n belong to natural number set. Now, you see, what is this? When n equal to 1, I have A1. When n equal to 2, I have A2. So this set has a special name. It's called sequence of sets. Sequence of sets. So this one has a name actually, okay? Special name for this case. Index set becomes sequence of sets. You see, index class of sets becomes sequence of sets. Because mostly, most of the cases we use this case, delta equal to n, delta equal to z, okay? But in general, of course, we can say delta is equal to r, delta is equal to q. In general, can, but that one is used for very complicated investigation of the sets. But for the ordinary case, so this is the sequence of sets. Okay, now look, open sets, the theorem says, open intervals, open subsets of real numbers have the following properties. Open subsets of real numbers have the following properties. The set Q, MT, and R are open set. Any intersection of a finite number of open sets in R is open. Any union of, you see, please pay attention, any intersection of the finite, pay attention, here finite number of open sets, finite number of open sets. Open sets is open. Any union of arbitrary collection of open sets in R is open. Okay? Interesting point, pay attention. This theorem says the set MT and R are open set. Okay, I will prove this. Proof is actually nice proof. Now, next interesting point, after close it. Now look, the set MT and R are closed. So MT set and R set in the first theorem says they are open set. In the second theorem says it is a closed set. It looks like contradictions, but you will see the proof is very nice and both of them are correct. Correct. According to the proof, the definition of the proof, we can say they are both open, they are both closed. So this is only the for R and empty set. Then please pay attention. In the closed set, the union of finite, any union of finite number of closed set is closed. But any intersection of arbitrary collection of closed sets in R is closed. So these two theorems is very important theorem. And only one part I will prove now, and because time is getting end. But the second theorem actually comes very easily can prove. But the first theorem, why any intersection of the finite number of open sets in R is open. Look, just before proof, I show the one example. Look, example 1. Let's say Qn is given the one example. Please, I am just explaining from this example, then prove the theorem. Will be much more easy. Okay, it is a set. I'm talking about sequence of sets. N from N. Okay, now if we consider this set and consider the Qn intersection. Okay, let's say here I will say K from 1, look, K from 1 up to N, QK. Okay, please pay attention. What is this? Q1 intersection Q2 intersection and Qn. Okay, Qn. Actually, O. Actually, this is On. Actually, not Qn. Better On. Anyway, so what is the n equal to minus 1 1 intersection 1 over 2 minus 1 over 2 1 over 2 intersection and etc. You see, I am just showing the one interesting point. Why we uh, in intersection minus 1 over n plus 1 over n. I am considering just n intersections of the open set. I am considering open set. So this intersection gives Q2. Q2. This intersection gives Q2. So Q2 intersection Q3 gives Q3. Intersection Q3 with intersection Q4 gives Q4. And so on. So in general, intersection of Q1, Q2, and Qn actually gives Qn, which is this set, minus 1 over n plus 1 over n. You see, the last small sets actually is the intersection of all these sets. Now, if I take limit from this, look, if I take the limit, limit n tends to infinity, intersection k from 1 up to n qk, which is qn as n tends to infinity. So look, getting smaller when n tends to infinity, it is just 1.0. 1.0 and 0, only 1 point is not open set. It is closed set. Okay, so that's why but this one is open. If I take finite intersection, you see, please pay attention. If I am taking finite intersection of the open set, then it is open set. But if I take any infinitely many open sets, it might not be open set. It might be, it might not be. So it means we cannot confirm that any number of intersection of open sets is open set. We cannot confirm that. But if we have finite, then we can confirm. So this is the one nice example for the contradiction of the any. You see here, any union of arbitrary collection of open sets in R is open. But for the intersection, we should put finite number of open sets. Okay, that is one good example to say that any union, any intersection of arbitrary collection of open sets in R is open. We cannot say. Okay, this is counter example. Counter example. So okay, the proof actually very also nice. Just let me prove and finish. Or you have the class. Do you have class or not? Hello? Can I finish?
For me, okay, doctor.
Okay, because we started very late. So just you know, how we can prove? Let's say O is a sequence of the sets Q1, Q2, and Qn. Okay, be the finite collection of open sets, and S is k from 1 to n q k. Okay, or OK, actually OK. I am always saying QK. Actually, O. This one all O. The OK. Okay. Now I will take 1 point from S. If I take 1 point from S, and this is the intersection, so if X belong to the S, then X belong to one of the QK. What we call it? Then X one belong to the QK. No, not one, because this intersection. So the X must belong to QK. Intersection of all, it must belong to the Q1, Q2, Q3, and so on. So it means it might be belong to all of the QK. So that's why you see from this, then X for all K. You see, for this one, for all K from 1, 2, and etc. N. Okay, then this neighborhood X minus epsilon, you see, please pay attention. X minus epsilon K, actually, epsilon K, corresponding epsilon K. Since QK is open, this one is open. Once it is open, there exists, by the definition, there exists epsilon K such that this set is what we call it, open set. This open set completely belong to QK. So if we take epsilon, you see here, important one, minimum of epsilon 1, epsilon 2, and etc. epsilon K, epsilon N, minimum. You see, if we take the minimum, then this X minus epsilon, X plus epsilon is a subset of X minus epsilon K and X plus epsilon K. X plus epsilon K. But this one lies, this interval actually lies in the QK. Okay, actually, okay. If okay, then this interval also belong to the QK. So it shows, you see, if this one belong to QK, so QK is open set. QK is an open set. This, hence the union, therefore S is the open set. So if you see the X minus epsilon, X plus epsilon is this interval belong to the QK, means the intersection of the QK is open, which means S is open. Therefore, S is open, and thus any intersection of finite number of open sets is open. Okay, and for the last case, you see, we are taking the X from the infinity union of Gn, or a sequence of Gn. Okay. Now, if X belong to the union, X belong one of the sets, which is G alpha. Since G alpha is open, there is epsilon such that this interval is belong to Gm. This implies this interval belong to the union, infinity union. Hence, this union is open set. It completes the proof. Actually, that is a important theorem, but proof is very clear picture. Once you know the picture of this proof, then you can easily prove the next theorem using this De Morion's law. Please This theorem, you will prove it. Next, tomorrow, I will ask you. Huh? Because it is, the second theorem is much more easy because of the law. Okay? I hope with this one, I am going to finish. Now, if you don't have any questions, I want to stop sharing. And if you have anything, please welcome. Otherwise, so see you tomorrow. Do you have any suggestion, questions? You see?
Doctor,
Yes, Anne?
attendance, Doctor.
Oh, attendance, actually, I have, when I given already, you didn't do, huh? Okay, let me, one moment in that case, one moment. Who are not signed it yet, please you sign. Then you can out. So academic. Okay, one moment. The model pin sharah.
And then one more thing for the group assignment, can we find our own members?
Yes, yes. You therefore you ask your friends to give you their own groups, okay? Own names.
Okay, Doctor.
Then you will just collect. Every group must be minimum the maximum of 5. One group can go the 6, minimum 5. Okay, now I am going to ask you sharing. So okay, tomorrow it is not compulsory, but next week is compulsory. Okay. Okay, please do sign or register and finish. You can leave. But Anne, please tell the students they should come. You know, at least few of them should come because a lot of good facilities, and we have to teach a hybrid, and the final exam mostly the face to face because it is said, I haven't discussed it yet properly. It is said that final exam, if there is a very positive reason, we have to bring, you know, the application to the faculty. Faculty should approve and send to the vice chancellor of academic. If they approve, then we can make it online. Otherwise, offline actually, because most probably offline. I will talk to Prof. Roslan, but if need to bring, we have to write application and may not be approved. I do not know.
Okay, Doctor.
Okay, please do sign and finish. Yeah, very cold. Very cold. I'm getting cold. Very big room, nobody. You can see empty.